The transition of humanity began not with the expansion of the brain or the use of tools, but with the establishment of bipedalism. To understand our current form, we must journey into the age of our ancestors, the Australopithecines. The initial breakthroughs established Australopithecus as the critical link between apes and humans, driven by fundamental changes in locomotion. The first chapter of human evolution began in 1925 with Raymond Dart's discovery of the Taung Child. Dart named the fossil Australopithecus africanus, arguing it represented an intermediate stage between living apes and humans. The specimen was revolutionary because its jaw lacked the typical ape diastema, and the orientation of its skull suggested an erect posture, marking the genesis of the Australopithecus genus. In 1995, Meave Leakey's team discovered 4.2 million-year-old fossils in Kenya, naming the species Australopithecus anamensis. This species is believed to be ancestral to Australopithecus afarensis. The most compelling evidence was a tibia fossil 4.2 million years ago, which showed the distinctively human structure where the joint surface is orthogonal to the shaft's axis. This indicated habitual bipedalism and pushed the origin of upright walking back by over 500,000 years. Anamensis exhibited a mosaic of features, primitive traits like a long, robust canine root, and an asymmetrical third premolar, alongside derived traits common to later Australopithecus, like thick molar enamel. Lucy, 3.2 million years ago, fully documented the anatomical adaptations for bipedalism. Analysis by Lovejoy showed that Lucy's ilium was dramatically shortened and rotated compared to chimpanzees, initiating the functional switch of the gluteal muscles from propulsion to pelvic stabilization. Lucy's long femoral neck increased the mechanical advantage of the stabilizing gluteal muscles. Furthermore, the internal structure of her femoral neck was optimized solely for the compressive stresses of upright walking, suggesting it was mechanically unfit for proficient climbing. The 3.56 million year ago footprints preserved in volcanic ash unequivocally demonstrated human-like locomotion, showing a clear heel strike and an adducted hallux. Despite these advanced adaptations, afarensis retained remnants of arborealism, such as long forearms and curved finger, toe bones. This debate over a mixed locomotor repertoire suggests that hominins diversified their survival strategies within a heterogeneous environment of forests and savannas. The transition to the genus Homo was marked by a complex, non-synchronous acquisition of human-like traits. The Australopithecus epoch was the time before the explosion of intelligence. The mean brain capacity, 400 to 500 cubic centimeters, was only slightly larger than that of chimpanzees, confirming that significant cognitive expansion had not yet occurred. The true turning point was foreshadowed by Australopithecus sediba, 2.0 million years ago, which showed a critical mosaic of ancestral and descendant features. Analysis of hand fossils showed sediba had a long thumb and human-like wrist morphology. This supported a powerful precision grip suitable for Oldowan toolmaking. Sediba's pelvis evolved to be Homo-like, but this adaptation occurred before the notable increase in brain size, 420 cubic centimeters, demonstrating that the transition to Homo was non-synchronous across the body. The blurry line between Australopithecus and Homo led to fierce debate. Bernard Wood and Mark Collard argued that existing Homo classification criteria were inadequate, proposing that Homo must be a monophyletic group sharing a single adaptive strategy. They argue that habilis and rudolfensis possessed primitive adaptive strategies more akin to Australopithecus, and should therefore be excluded from Homo. Instead, they claim the earliest true Homo was Homo ergaster 1.9 million years ago. This species began a new adaptive strategy: larger body size, obligate terrestrial bipedalism, and a relatively reduced masticatory apparatus. The explosion of intelligence was initiated by the relatively larger brain of H. habilis, but its full meaning, evidenced by greatly increased brain capacity 850 cubic centimeters and the development of sophisticated tool cultures, was cemented after the emergence of H. ergaster. Earliest Homo debate was complicated by the 2.8 million year ago discovery of the LD350-1 mandible, suggesting an even earlier origin for Homo. Although its classification remains highly contested due to comparisons with Sediba's morphology, the Australopithecines flourished within a heterogeneous mosaic environment. Anamensis's home at Canopoi was a mix of riverine forests and shrubland intermingled with grasses. This environment supported megaherbivores, including 5 species of elephants. Anamensis largely relied on resources, fruits, and leaves. Laetoli was similarly a mosaic of open plains and tree cover, dominated by the footprints of Madoqua and hares, rabbits. These valuable animal track records are crucial for paleoecological research, but are critically endangered by erosion and livestock grazing. The Australopithecus epoch irreversibly changed the direction of human evolution by establishing two-footed walking. Their mosaic adaptations offer profound insights into the complex, gradual process of anatomical redesign that preceded the ultimate revolution of tools and intelligence. The journey continues.